So today we're going finally, after spending so much time in section 4.2, we're going to go into section 4.3, which is called Similarity. So in this section, we're going to be dealing with what's called a linear operator. I think you've seen this term in your homework. What it means is just all it is a linear transformation where the domain and range are the same. Okay, so it's going from B to B. Okay. So so you have a linear transformation going from the vector space back to itself, and you have some basis B, okay, and we will think about their matrix representations with respect to these bases. Okay, so so you use the same basis on both sides. Okay, so so here you have some vector v, and it gets mapped to its coordinate vector with respect to the b basis, and we use the same map on both sides. Okay, so maybe if we called it p, we're going to call it'll be p the same on both sides. Okay. Okay, and just for notation, we'll let A sub B, denote the matrix representation of T with respect to B and B. Okay, so on both sides. Okay. Okay, so that's the setting. Okay, and we'll ask the following question. So notice if we change the basis B, we get a different matrix. We get a different matrix representation of T. Right, so if we have another basis, suppose you have another basis B prime of V, then that would give you a different matrix representation, right? You get change B to B prime, you would get a different matrix representation, AB prime, right? And the question is, what's the relation between these? What's the relation between these two matrices? Two matrices. Okay. Has anybody read ahead? Anybody know the relation between these two matrices? It turns out that these two matrices are related to each other in kind of an interesting way. Anybody read ahead? No? That's okay. 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 Before we answer the question, let me review one idea. So we need to review one notion. So remember this: given a vector space, so the notion of transition matrices. The notion of a transition matrix. Okay. So given a vector space B and two bases E being V1 through Vn, and basis F being, say, W1 through Wn, and Wn, both of the same vector space. we found the transition matrix taking the coordinate vector with respect to E to the coordinate vector with respect to F. Okay, remember this, right? Here's a picture. You have some vector space V. You have some vector space V, and you have the coordinate vector map, right? V goes to coordinate vector with respect to E, right? Right. So that maps you from V to Rn, right? But you also have another coordinate vector map, right? V goes to the coordinate vector with respect to F. Okay, right. And we figured out there was a matrix that took you from V sub E, the coordinate vector with respect to E, to the coordinate vector with respect to F. Remember this? Right. Does anybody remember the matrix? How do we get that matrix? How do we get that matrix? Anybody remember how you get that matrix? Yeah, Lizzie.
Wait, so we're going from which one to which one?
We're going from E. We're going this way, from
Okay.
E to F.
E to F.
Yeah.
Then it's the inverse of the basis of F times the basis of E.
Well, so you're thinking. So remember, this isn't Euclidean space. This is not
Okay.
Euclidean space.
Right.
So it's a little bit. It's not so simple as that, right? Because these guys are not Euclidean vectors. You can't make a matrix out of these guys.
Okay.
Right? These aren't Euclidean vectors. Okay, Ross. Yeah.
I'm not quite sure.
That's all right.
Yeah. So you just represent like V1 into like the combination of W1 to Wn.
Yeah.
And you find like the coordinates.
Yeah.
And the coordinates is the column of the matrix.
That's right. That's right. So you remember you had to go through this thing. You took the elements of your initial basis, right? You expressed each element of your initial basis in terms of the target basis, right? So you got like A11, W1 plus A21, W2 plus A N1, Wn, etc. The n was 1n, W1 plus A2n, W2 plus N, right? And then the matrix S, which was A11, A1n, AN1, ANN, namely the transpose, right? These things turned out to be the first column, right? The coefficients for the first vector of the first column of your transition matrix, et cetera, et cetera. This thing was the transition matrix from E to F. Okay. This is the guy who took coordinate vector in E and gave you back the coordinate vector in F. Everybody remember that, or at least feel like you've seen it before? Okay, so okay, so now let's write down the answer to the question. What's the relation between these two matrices? Let me write it over here. We'll need some space to explain it. So here's the theorem. Let me just write it down in full. Suppose you have a linear operator and you have two bases, v1 through vn, w1 through wn, both bases of v. Let S be the transition matrix from E to F. Maybe it's useful to write it like this. So I could write it S sub EF, since it's going to indicate that it's going from E to F. Okay. Then, okay, so let A sub E be the matrix representation of T with respect to E and E on both sides. Let A sub F be the matrix representation of T with respect to F and F on both sides. Okay, so then our question was, what's the relation between, right? What's the relation between these two representations? And the answer is that A sub E is going to be S inverse A sub F S. Oops. Lizzie, what is it?
Wait, what do A sub E and A sub F represent?
Okay, so remember what we're talking about? Let's remember what we're talking about, right? We have T going from V to V, right? We have bases. We have two bases: the E basis and the F basis. Right? We have the F basis, right? Each of those creates a coordinate map,
Okay.
Coordinate vector map, right? Right? A sub B is the matrix representation of T with respect to E and E on both sides. Okay. A sub F is the matrix representation of T with respect to the F basis on both sides. Okay. Right. So you've got these two representations of the same linear transformation. Right, and we're asking, what's the relationship between these two guys? Well, it turns out that that one is what's called the conjugate of the other. Okay, so they are what's called conjugates. They are conjugate matrices of each other. Yeah, Avery.
I'm confused about one thing. Since we proved the community property, I'm not sure which property it is, the one that says that AB times C is the same as AC times B, or
we have the associative property.
or the associative property.
A, B, C equals A, B, C. Yes.
So then why couldn't you rearrange? Oh, wait, never mind.
Yes.
Yeah.
Right. There is, matrices don't commute, right? That's the one
right.
That's the one we don't
Okay.
have, right? So yeah. Yeah.
Because I was going to say it would be the identity
Yeah.
matrix, but that
No,
doesn't
it's
apply.
not true. Yeah. Okay. Okay. So everybody getting what we're doing, right? We have a linear transformation. I mean, it's a linear operator, and we have its matrix representations. We have two matrix representations of it. We're saying that in fact these guys are related to each other, right? They're not just random matrices. There's actually a relationship between them. One is one is so-called conjugate of the other. That is, there's a matrix so that you can multiply this guy by the inverse and the matrix on either side, and then get to AE. Okay. 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 So, why does that happen? Let's explain how that happens. So, maybe I'll ask you. So I can either show you an example of this first, and then explain how it works, or I can explain how it works and then show an example. Do you have any preference?
Explain how it works.
Explain how it works and then example. Okay, that's actually how I prefer to do it myself. But, that's fine with me. Okay, so why does this? Proof. Okay, so consider the following diagram. Okay, so we've got T going from V to V. We have our the map taking V to the coordinate vector with respect to E. And we have also the map going from V to the coordinate vector with respect to F. Okay. Right. Right. So we call this map P. Let's call this other map P prime, say. Now, AE is the matrix AE is the matrix representation of T with respect to the E basis, right? So in other words, we can go this way or this way, right? Right, we can go, like we said last time, if we go across, it's the same thing as going all the way up and down. Right? Because this is the matrix representation. Okay. A sub F, right? Maybe I'll just write A sub B. Okay. A sub F is the map that so that we can go this way, right? Maybe this is not making sense. Let me just say it this way. Okay. Okay, let me just leave this out. Yeah, Julia.
The V with respect to F, or with the basis F, is a vector, right?
Yeah.
Okay.
Yeah. Okay. So okay, so remember what these things are, right? The matrix representation with respect to E means that you can go this way or you can go this way and you get the same thing, right? The matrix with respect to F means that you can go this way or you can go this way and you get the same thing, right? Okay, so if you look at this map here, what's this map? Going from V sub E to V sub F, well, that's the transition matrix taking you from E to F, right? this map here, going from here to up to here, that's the guy that takes v sub e to v sub f. That's you multiply by the transition matrix with respect to E, F, right? This guy here is the opposite guy, right? So it will be the transition matrix, the inverse. It will be the inverse of the transition matrix, right? Because, right, this map, going from, this will be going from Vf to V sub E, right? So it's the inverse of the transition matrix that takes you from E to F. Okay, so what you see is that since the diagram commutes, what you see is that if you do SEF, follow it by AF, and then follow that by SEF inverse, right? Then that's the same thing as going across AE. So, right, the point is that in this diagram, basically, if you go all the way around this way, if you go from Rn to Rn and then across and then down, you get the same thing as if you go directly across. Okay, because these guys are the matrix representations. Okay, so if you look at what that means, well, that means that if you do this guy first, follow it by A sub f, and then do that, that's the same thing as just multiplying by A sub e. Okay, right? Or you could say it the other way, right? You could also say that AF, just going across from here, you could go down this way, right? You could go down this way, across, and then back up. Right, so what would that say? That would say that's SEF inverse followed by A sub E followed by SEF. Right. Okay. So one way of thinking about this, I don't know if this is helpful or not, but you think, well, if I have the coordinate vector of something with respect to E, and I multiply it by this AE matrix. Well, let's look like this. If I have the coordinate vector of something with respect to E, and I multiply it by SEF, well, what does that give me? That gives me the coordinate vector with respect to F, right? And then suppose I hit it with A sub F, right? That says, okay, I'm going to act on it with the operator. I'm going to act on it with the operator. And then I'm going to switch it back. So I move it to the F coordinate system, I hit it with the representation with respect to f, and then I switch it back to the e. I switch it back to the e coordinate system, right? Right. That's the same thing as just staying with your coordinate vector with respect to e and hitting it with the transformation. That will be the same thing as hitting it with transformation over here. Okay, right. So here you take your guy, you translate it to the f coordinate system, hit it with the transformation, and then switch it back to the e coordinate system. Right. That's the same thing as just staying in the e coordinate system and hitting it with the transformation. Okay. So I don't know if that's helpful, but that's actually really what's going on. So, okay. Okay, in any case, the point is that since on this diagram, going any way around it, we'll end up with the same thing. That gives you that these things are the same. Okay. Any questions? I feel like it's maybe not getting through. Can anybody have a question?
We just do an example.
Should we do an example to
Yeah.
make it concrete? Okay, maybe that's the way to do it. Well, actually, let me talk to each other for one. Let me give you a chance to ruminate. So, talk to each other for a minute and see if you can come up with a question if you can.
Like still in the hole.
Just not in general.
Sounds right.
Well, I feel like that's like makes sense.
I feel like I understand the diagram of the equation, I'm just not sure what we're gonna do with it. Yeah, exactly.
That actually makes me feel pretty good.
It makes sense.
Yeah, the diagram's really helpful. I'm glad we did the proof first.
Yeah. I mean, you're just following the paths. You gotta remember you can go both ways on that. So
I guess I'm just wondering what its application is, because I feel like it's just another way of getting to.
So the point is, what we're trying to say is that AE is the same as just going that way, using the SCEF thing.
Yeah.
yeah.
I think I need to.
Isn't it just there's a shortcut and then there's a long way and they're equal? But
Yes,
then
yes.
what is the point of knowing that?
Okay.
I hope that wasn't rude.
No. That's fine. Okay.
What are yeah.
Okay. Anybody have questions? So we have one right here. Say it again, Avery.
What is useful about knowing this?
What's useful about knowing this? Okay. Well, you'll see something pretty cool. Hopefully by the end of the class. But the point here is just that that your transformation can be represented in different ways. Okay. And those representations actually are related to each other. Okay. So that's sort of the main thing. Let me give some terminology that will allow us to talk about this a little bit more clearly. Okay. So some terminology. Okay. So here's a definition. Say A and B are square matrices. If there exists some matrix S, some square matrix S, such that B equals S inverse AS, then we say B is similar. Oops. B is similar to A. Okay. notice that B is similar to A. If B is similar to A, then A is similar to B. Right? Because if B is S inverse AS, right? If B is S inverse AS, well, then you know that A is S B S inverse, right? In other words, A is S inverse B S inverse, right? So, right? So, you know, if there's a matrix you can conjugate by and get to B, then there's another matrix you can conjugate by and get back to A, right? Namely, the inverse matrix. It's also true that if A is similar to B and B is similar to C, then A is similar to C. Okay, so so similarity, the way we say this is that similarity is an equivalence relation. Similarity is an equivalence relation. Just like row equivalence, do you remember row equivalence was an equivalence relation? Okay, so so what this is saying over here, so the theorem says then that if A, E, and F are matrix representations of T, then they are similar matrices. Okay, that is, any matrix representations are going to be similar to each other. In fact, it's true that if any any matrix if A is a matrix representation of T, then any S inverse AS is also a matrix representation of T. Okay, so I'm not going to talk about this. You can read it in the text if you want. But the point is that so that each matrix corresponds to a whole category of similar matrices. Okay, so like you take your similar matrix and you conjugate it by all invertible matrices, right? That'll give you all sorts of different representations. All of those things turn out to be representations of your matrix. Okay, so you know what we're going to do soon is to try and find the way of finding the simplest matrix representation. Okay, so right, you've got your linear transformation, and then you've got all these possible matrices that represent it, right? Yeah, and some of these matrices will be simpler than others. Okay. Okay. Let me do the example, and that will make all of this clear, I hope. Okay. So examples. Okay. So let D be differentiation on P3 on the polynomials of degree less than 2. Let B be, as usual, 1xx squared. Okay. Then the matrix representation of D with respect to the B basis is going to be 0, 0, 0, 1, 0, 0, 0, 2, 0. Okay. Right. You know how to get it, right? You differentiate, you take d of 1, d of x, and d of x squared, and you represent them with respect to the B basis, right? And you get the columns. You get the columns of your matrix. Right? Okay. So the problem, maybe I'll let you try it. Use the transition matrix. Use the transition matrix S from 1, 2x, 4x squared minus 2, 2, so let's call this guy B, and let's call this guy B, 2, 1x, x squared, to get the matrix representation of T with respect to the V basis. Okay, so I want you to see if just maybe set up the calculation to get A sub B. Okay, even if you haven't finished it or started it, talk with somebody and explain how to do it. How do you find A sub V using this transition matrix?
Okay, so we have A, B, and we're going to left multiply by the S. Which I think we find that we get from V to B, and then we left multiply A, B, by the inverse of that, and then multiply by
Okay, does anybody want to walk us through it? Nico, I feel like you know what you're doing. I mean, I didn't listen so closely, but you sounded like you know what you were talking about.
Okay, well, I'm not sure if this is
Yeah,
right.
okay.
I was thinking we have in the diagram that the AB that we had is analogous to the AE,
Mhm.
and the AB is analogous to the AF.
Sure, yeah.
So then we're trying to do the, like we need to know what the S is,
Yes.
which I think is the coordinate, I guess like the matrix.
The transition matrix?
Transition matrix that goes from V to B.
From V to B, exactly.
So,
Right, so
then we're going to multiply on the left by the, multiply like inverse of that times AB, and then times on the right that.
yes. So we want AV, right? We want the representation with respect to V, and we have the representation with respect to B, right? We have the representation with respect to B. Well, how do we get the representation with respect to V? Well, you need to multiply by the guy that goes from V to B, and the guy that goes from B back to V. Right? Okay. So what do you do? Right? You need to. We want S sub VB. Right? S sub VB. Right? Well, to get that, we need to express each of these guys, 1, 2x, 4x squared minus 2, in terms of these guys, right? In terms of the B basis, right? Well, that's easy, right? This is 1 of 1, 0 of x, and 0 x squared, right? This is 0 of 1 plus 2x plus 0 x squared, right? This one is, of course, negative 2 times 1 plus 0x plus 4x squared, right? So you take those coefficients and you use these guys as the columns, 0, 2, 0, 2, 0, 4, right? Okay, and then you work it out, right? SVB inverse is going to be something. It turns out to be 1, 0, a half, 0, 1 half, 0, 0, 0 quarter. And then you conjugate, and you work it out, and it turns out that this thing is 0, 2, 0, 0, 0, 4, 0, 0, 0. Yeah?
Why is the 1, 3 entry of SVB 2 instead of negative 2?
Oh, it should be negative 2. I'm sorry. Thanks.
Then shouldn't the inverse be negative?
No, it's actually just a half.
Okay.
Okay. So, and we can check this. If we calculate a sub b directly, right? We could calculate a sub b directly by looking at the derivatives action on these guys, right? D of 1, D of 2x, and D of 4x squared minus 2. Right? This is 0, this is 2, this is 8x, right? Right? And you see that if you take 0 and express it with respect to the v basis, you get 0, 0, 0. If you take 2 with respect to the b basis, it's going to be 0, 2, 0, right? And 8x with respect to the b basis is going to be, I'm sorry, this is going to be 2, 0, 0, and 8x is going to be 0, 4, 0, right? And those are the columns that we got here. Okay. Okay. So what you see is that matrix representations with respect to different bases are actually related. They're actually similar to each other via the transition matrix. Okay. Now, this is not the cool thing that I was hoping to show you that would sort of explain why we are interested in this. Okay, this is just showing you that it actually works. Okay, but next time we'll start off with an example where you'll see that this is actually something pretty useful. Okay.